Hello class, we are continuing our 3.6 notes, curve sketching. Hopefully I'll do both of the last two problems tonight, we'll see. And we're looking at example 3, this is what we're graphing. So we have f of x equals x divided by the square root of the quantity x squared plus 2. So our pre-calc stuff doesn't help us as much on this. First I want to think about x-intercepts and y-intercepts. So remember, our x-intercept comes from the numerator equaling 0. So that's going to be at 0, 0. Our y-intercept comes from putting in 0 for all of the x's. And so 0 over square root of 0 squared plus 2, 0 divided by anything, still 0. So it always makes sense if you get 0, 0 for your x-intercept, your y-intercept also has to be 0, 0. So the end behavior on this one is a little bit weird. Asymptotes don't really make sense. I might think about what kinds of numbers I can substitute for x, but because I'm squaring it and then adding 2, this one's a little bit unusual for a square root. So with square roots, I have to remember that the x squared plus 2 part, whatever is inside, has to be greater than or equal to 0. And when I solve this, I would get x squared greater than or equal to negative 2. Well, that's always going to happen. When I square a number, it's always going to be positive. So when I'm looking at my domain is going to be negative infinity to infinity. So that's not going to be an issue here. So instead, we're going to look at end behavior. So the way we're going to look at end behavior by thinking about what's happening as x approaches infinity or x approaches negative infinity is by using limits. So we are going to find the limit as x approaches infinity of this fraction. And we did some of these on your homework a few nights ago. This is that trick we used where x is my highest power here because square root of x squared is going to be absolute value x. So I'm going to divide everything by x, all those little parts. And inside my square root, it's really an x squared. And then we will simplify our fractions. So now we have 1 over the square root of 1 plus 2 over x squared. And then we recognize that 2 divided by x squared is a really, really small number. And as x approaches infinity, this is basically 0. So we have 1 over the square root of 1, which is just going to be 1. And in a similar way, we could prove that the limit as x approaches negative infinity of this function is going to equal a negative 1. So when we're looking at negative infinity, the big difference is that the square root of x squared, because that's an absolute value, we know it can be a plus or minus x. So when we look at a positive infinity, we're going to use a positive x. When we use a negative infinity, we're going to use a negative number instead. So these limits are essentially going to give us asymptotes. So as we go to the right or to the left, we're going to get closer and closer to those numbers. So I'm going to change my scale a little bit here because 1 is almost hard to graph so close to the x-axis, and I'm going to make this one 1, and this will be 2, this will be negative 1, and negative 2. Just give myself a little bit more space. And I'm going to go ahead and dash in those lines. And I know my whole function has to be between those two, right? So as I go to the right, it's going to go towards positive infinity, will be towards 1. And as I go to the left, my y value will get closer and closer to negative 1, and I have a point in the middle. So at this point, I kind of have a good idea about what the graph looks like, but we're still going to do all of these steps and investigate this function. So my first derivative, I would have to do low d high. So low is x squared plus 2 to the 1/2 power. Derivative of the high is 1 minus high d low. So x times 1/2 x squared plus 2 to the negative 1/2 power. And something wild just happened here, to the negative 1/2 power, and then times a 2x. just totally ran out of space there. It looks terrible. We'll fix it on the next line. And then this is all over x squared plus 2 to the 1/2 and then squared. All right, let's fix this numerator up a little bit. We've got x squared plus 2 to the 1/2 and then minus. So we had a 1/2 and a 2, and we've got those x's times x's, and I still have a negative 1/2 power. I might have tried to do a little bit more at first, but it was so messy it was really hard to follow. And then this is now first power. 1/2 times 2 is first power. So I'm going to, there's different ways I could handle this. I could make this part into a fraction over here and then multiply to get a common denominator, or I could factor. I kind of like factoring. If that method doesn't work for you, let me know and we could try something else. So I'm going to factor out the negative 1/2 power. And if I have this first part here, and I'm factoring out a negative 1/2 power. Remember, when I'm factoring something out, I'm essentially subtracting it. So my power is 1/2 minus a negative 1/2 is first power. So let's think about what's going on there and why this is first power. So if I was going to multiply this one back in, remember when we're multiplying in, we're adding our exponent. So negative 1/2 plus 1 makes it a 1/2. So it totally works. And then when I factor all of this stuff, when I factor out the x squared minus, or x squared plus 1 to the negative 1/2 power, that's just gone. And I'm left with a minus x squared. So this is all over x squared plus 2. And this is, of course, first power. So this negative exponent part's going to go in the denominator. It'll make it a positive exponent. So my new power would be essentially 1 plus the 1/2, which is x squared plus 2 to the 3/2 power. And x squared minus x squared would leave me with just a 2 here. So when we are finding our critical numbers, we're looking for where our numerator is equal to 0, which cannot happen because that's when our function's equal to 0, when our derivative of our function is equal to 0. We also want to find when our derivative is undefined, but just like we showed at the beginning, because this is being x squared, because x is being squared, I don't have to worry about my function being undefined. My denominator is never going to equal to 0. I'm going to be able to take a square root, so there's no issues. So I have no critical numbers here. So no critical numbers means we don't have any maxes or mins. All right, next job is the second derivative. So let's go ahead and take that. So my second derivative, in fact, I'm going to rewrite my first derivative, and I'm going to rewrite it because now my numerator is only a constant as 2 times the quantity x squared plus 2 to the negative 3/2 power. So now when I take my second derivative, I can just do chain rule. So my second derivative, I would multiply my exponent in front and subtract 1. So negative 3/2 minus 1 is now negative 5/2. And then times derivative of the inside. So my inside function is just the x squared plus 2. So derivative of that is a 2x. And let's see, we end up with a negative 6x times the quantity x squared plus 2 to the negative 5/2 power. So negative 6x divided by the quantity x squared plus 2 to the 5/2 power. All right, now we have something to work with. So when we look at our possible POIs, we're doing the same thing as before for our possible POIs. We do numerator equals 0 because we're looking at when our second derivative is equal to 0. Well, that's when the numerator equals 0. So x equals 0. And we look at when our second derivative is undefined. So that's going to be like when our denominator is equal to 0. But we do not have to worry about that denominator being equal to 0 because, again, it's never going to be undefined. We're never going to be taking the square root of something that's negative. So we're fine here. So there's going to be none from this. So all we have to worry about is x equals 0. So we're going to go ahead and plot that. And we want to look at a number that's positive. We want to look at a number that's negative. So if I put in a positive number, say positive 10, into my second derivative, remember we're plugging back into the second derivative. This is a second derivative chart. We're looking for concavity, possible POIs. So if we put in a positive 10, my denominator is always positive no matter what. I don't have to worry about it. But my numerator would be a negative. Negative 6 times a positive 10 is a negative. And if I put in a negative value for x, the reverse will happen. I will get a positive. Negative times negative is positive. So this is telling me I have a POI at 0, 0. I'm going to write it over here. So point of inflection at 0, 0. And we are concave up on the interval from negative infinity to 0. And we are concave down on the interval from 0 to infinity. So all that's left is to draw in our shape here. So we're going to do a concave up part here. Oh, got to put my marker back on. And then a concave down part over here, where I've got a slight point of inflection there in the middle. So it's kind of an interesting graph. Not maybe what you would expect here. They're kind of cool. It's neat to look at some of these different graphs that we haven't seen before in different classes. And I really love seeing all of these things come together. You know, thinking about domain and range from before, looking at what's going on with our intercepts, like all the pre-calc stuff, like finding a limit and showing that to get our end behavior, doing our first derivative, looking at critical numbers, our second derivative. It's really cool, I think, to see how these problems come together. All right, I'm going to go ahead and stop this video, and example 4 will be on the next one. As always, if you need help, please make sure you ask.